Morning, everybody. Let's give this a shot. What we're going to do is it's the day after IASIS, and we have people at all different parts. So what I'd like to try and do is a screencast on the Feynman diagrams to give the people that were here a chance to work ahead a little bit and give us some time for the people that were away to catch up. So last class we talked about creating energy out of nothing, essentially, and the Heisenberg uncertainty principle, and how it allows us to, or us or particles or anything, to create an energy delta E out of nothingness for a very short period of time, delta T. And if I scroll up here, I'll find a few slides up. There we go. That's the formula that it was based on, and we have this is our final product. Delta E times delta T is h over 4 pi. Right? That's the Heisenberg uncertainty principle. Now, these particles that are created out of nothing, they only last for a finite period of time, and so there's a range or a distance that they can travel. All right, and what we're going to do is we're going to use the Heisenberg uncertainty principle to find that range. So we're starting out with the formula delta E times delta T equals h over 4 pi. You can see that the particle travels at a maximum of the speed of light, because nothing can travel faster than the speed of light, and it has an energy delta E, and I'm going to say that delta E energy equals mc squared from our old buddy Albert. And so what I've done is I've made delta E equal to mc squared times delta T equals h over 4 pi. Alright, scrolling down a little bit, what I've done on the second line, I've taken the mc squared and just turned it into m times c times delta T over equals h over 4 pi. Alright, and I've taken the mass times speed of light and I brought it over to the denominator on the right hand side of the equation. So now I have c times t equals h over 4 pi mc. Now c is the speed of light and t is the time, and so if you take the speed of light and multiply it by the time, you get a distance, and that distance is the maximum range a virtual particle or exchange particle can travel, because it can't travel faster than the speed of light. And so therefore c times t is a velocity times a time is a distance or a range. That's the farthest that particle can go, and that c times t, or range, equals h over 4 pi mc. So if you know the mass of the particle, the exchange particle that's created, you can use that information to find out how far it'll travel. Now generally photons and gravitons have essentially zero mass, so they can travel an infinite distance, which is why you are pulled by the Earth's gravitational pull, but you're also pulled by the Sun and Saturn and Jupiter and Pluto and things very, very far away from you. It's because gravitons essentially have infinite distance. Okay, same thing with electromagnetic charge. Okay, you are attracted or repelled by like or opposite charges an infinite distance away from you. With weak forces and with strong forces, that's not the case, though. Remember that in the case of nuclear stability, the strong force only holds for about 10 to the negative 15 meters. We learned that last year, and so you get a situation where protons are repelling each other in the nucleus, but they're attracted to each other if those protons are close enough to each other. And in the case of a great big uranium nucleus, the strong nuclear force only holds for neighboring nucleons, but the electrostatic repulsion exists for the whole nuclei, and that makes it unstable. Okay, so anyhow, that's the formula for range, and what I'm going to do is I'm going to use that to sum up exchange particles, or virtual particles they're sometimes called. Okay, remember that gauge bosons, or virtual particles, or exchange particles, it's a shame that they can't just give it one name, but are particles that are created from an energy delta E for a time delta T. Alright, and they have a whole number spin, so they can overlap each other in space and time, unlike fermions like quarks and leptons, which can't overlap each other at the same point at the same time. So listed below, and I'll post this up online so you can see the notes with more time, I have the four fundamental forces and the exchange particles that are linked to them. So you have strong nuclear forces with their delta E, or create what are called gluons. Okay, or gluons, I guess, essentially create the strong nuclear force. And we'll learn about gluons in a couple of days when we talk about quarks. But you can see all four of these exchange particles have whole number spins of 1, or in the case of a graviton, 2. Okay, the masses of these, I need to check this one. I think the mass might be bigger, but the mass is, most of the time when you deal with mass, you're going to deal with weak nuclear force, and I'll check this. I think that might be a mistake. The charges of these are 0 except for weak nuclear force. I'll speak about this in a few minutes. There's 3 particles for weak nuclear force. Thanks, George Bush. There's W minus, W plus, and Z0. And I'll show you in a few minutes how these charges are carried into neighboring particles, as is the case in beta decay. But I'll come to that in a few minutes. Relative strength shows, well, the relative strength as a comparison. Strong nuclear forces are much stronger than the rest. As you can see, gravity is quite a bit weaker, 10 to the negative 39 times the strength of a strong nuclear force. Electromagnetic is about 100th, and a weak nuclear force is about a 10,000th. And then finally, the range, 10 to the negative 15 for strong nuclear, 10 to the negative 18 for weak nuclear, because they're the largest particles. And then photons and gravitons can travel an infinite distance. Okay, moving along, because YouTube only gives me 15 minutes. Feynman diagrams. Okay, a Feynman diagram, I'll jump ahead so you can see what one looks like, and then I'll come back. These are Feynman diagrams, and they show the interaction between exchange particles and elementary particles. And so in drawing Feynman diagrams, there's a few simple rules. Arrows that point to the right represent matter. So skipping ahead, here's an electron with an arrow pointing to the right. That represents matter. Okay, our arrows pointing to the left represent antimatter. So here's an arrow pointing to the left. That's a positron. That's antimatter. All right. Wavy lines represent photons or bosons. So these are wavy lines. And I don't think I have, I could just draw it really quickly. A gluon looks like this. I don't think I have any examples with gluons today, because we deal with gluons in a little while. That's what a gluon looks like. Okay. The vertices between these particles, like this one right here, okay, that represents an interaction. That's where you get an exchange particle is either emitted by an elementary particle, so the delta energy creates a particle, or it absorbs a particle. That happens at the vertex. And then finally, I'm going to talk about this in a minute, the more vertices there are in a Feynman diagram, the less likely it happens. So some of the diagrams we look at, they only have one vertex. And so those diagrams happen quite a bit. That's stuff like an electron being repelled by another electron. Okay, that happens all the time. Okay, but you will see a diagram of photon-photon scattering where light repels light, and light doesn't repel light very often. As you know, waves generally pass through each other, and so that's a rare occurrence. All right, let's skip ahead and let's try some of these. All right, here we go. So here are 2 examples of Feynman diagrams. The first one, number 1, is an electron-positron pair production. So what we have is time moves from left to right, okay, and we have a photon moving through space from left to right. And all of a sudden, at this vertex, the photon becomes a positron, okay, and we know it's a positron because it's positive, and the arrow is pointing to the left, so it's antimatter, and an electron. An electron is matter because the arrow is pointing to the right. So essentially what you have is a photon moving through space suddenly creates a positron and an electron. Okay, one vertex, so it happens quite often. It doesn't last, but it does happen. The next one is the opposite occurrence, and usually if you have electron-positron production, you also have annihilation almost immediately following it. You have an electron moving through time, moving through space, with its arrow pointed to the right, and a positron, which is antimatter, moving through time and space as well. Remember, antimatter is denoted by the arrow pointing to the left. When an electron and a positron come in contact with each other, they annihilate each other, and so what you get created is a photon. Okay, skipping ahead. This one, okay, electron-electron repulsion. So this is one electron repelling another electron. So you have two electrons flying through space-time. This one here and this one here. Okay, and remember, time flows from left to right. The electron on the top releases a photon, an exchange particle, for an indefinite period of time. And so it goes out, and in that time, that photon is absorbed by this electron. And what does it cause it to do? It causes it to change momentum. When the photon is released, okay, again, to conserve momentum, the electron which was going this way is forced to change direction to keep momentum conserved. Remember, we talked about the astronauts in space. They throw their tool this way and they go this way. It's the same thing with the electron. It emits a photon going down and it's forced to go up. And it'll go up until it receives that photon back. In this case, it never gets the photon back, so it just keeps going up through space. The photon goes down through space, is absorbed by the other electron, which changes that momentum and makes it go down. So this created energy delta E has created an exchange particle called a photon. That photon is emitted by the electron on the top, absorbed by the electron on the bottom, and the resulting changes in momentum have caused the two electrons to repel each other. And that's the theory of standard model. They're saying that's how two negative particles repel each other. That's why it occurs. All right, let's skip ahead to the next one. Whoa, okay, this is the one I was telling you about. Photon-photon scattering, light does not happen very often. And here's why. With light scattering light, you have a photon moving through space, creates electron-positron pair production. So here's my photon going through space and suddenly becomes an electron with the arrow pointing to the right and a positron pointing to the left. That electron moves through space and absorbs another photon. Here it is here, and so it changes direction. The positron, moving through space, emits a photon and also changes direction, which causes the electron and the positron to collide, and annihilation occurs and creates a photon. And in so doing, you have this photon and this photon, which are going down and to the right and up to the right, have now changed direction and gone this way. So it appears as though the two photons have repelled each other or scattered each other. And it doesn't happen very often. And the reason it doesn't happen very often is it requires 1, 2, 3, 4 reactions to occur. And if we skip back to that slide, well, each reaction has a square root of 1 over 137 chance of happening. So for 4 of that, that's going to be that number squared. Okay, take 1 over 137, take the square root of that. So it's probably going to be in the ballpark of, say, 0.02, and then make that to the exponent 4. That's a very, very small number, and so this reaction is it's unlikely to occur. Okay. All right, here's one that we have seen. Okay, this is beta production. This is when you get a neutron undergoes beta decay and becomes a proton. Here we have, we'll talk about this in a couple of classes. Okay, this is a baryon. It's a neutron. It has 3 quarks in it, a down, and an up. This is a proton, and it also has 3 quarks, an up, a down, and an up. And what happens in beta emission is this. Essentially, one of the down quarks becomes an up quark. Now, down quarks have a charge of -1/3, and up quarks have a charge of +2/3. And the way this occurs is your down quark has to lose a negative charge, because it's -1/3, it becomes +2/3, has to lose -1. How do you lose -1? Well, you create an exchange particle with a charge of -1, like W minus, and then you lose it. Okay, so the down quark creates an exchange particle, a -W, which goes up. Okay, and then that -W has a range that you can calculate, and within that range creates an electron with a negative charge and an antineutrino for an electron with 0 charge. Couple things about this. Okay, charge has to be conserved because it's a quantum number, so -1/3